All right, now continuing on with the next example, example 30, the sum of two fair dice. So consider the experiment of rolling two distinguishable fair dice and recording the up faces. Now we've looked at that example in the past, but now we're going to define a random variable on that sample space. Let the random variable x be the sum of the two up faces. And so we want to do the same kind of things we did in the last example. We want to determine the sample space of x. We want to find the PMF of x and graph the PMF. And then we want to find the CDF of x and graph the CDF. Now recall that the sample space of this experiment, cap S, is the set of all ordered pairs, I, J, such that I varies from 1 through 6. And then for every, regardless of the value of I, J goes from 1 to 6 as well. Where the structure of the elementary event I, j is the following. The first coordinate is the number that is obtained on die 1, for example, the green die. And then the second coordinate is the number that is obtained on die 2, for example, the red die. Now the random variable x maps the sample space that consists of 36 values. It maps the values or the points in that sample space to the real line in the following way. The random variable evaluated at a point or at an ordered pair, I, j, is equal to I plus j. And then since the dice are assumed to be fair, the 36 elementary outcomes in the sample space S are equally likely. Now another way to think about this and to represent it is in tabular format. So I've got that represented here, and so I've got a table. The columns correspond to the outcome of die 1, which I'm calling the green die, and the rows correspond to the outcome on die 2, which is the red die. Now there are 36 cells in the body of this table, and in each of those cells I've listed the ordered pair that corresponds to that particular outcome. So for example, when die 1 is a 3, die 2 is a 4, then this would be the elementary outcome associated with that outcome. All right, and then because the dice are assumed to be fair, then all 36 outcomes are equally likely. The outcome in each one of these 36 cells has the same probability, which would be 1 over 36. Now, to calculate probabilities associated with this experiment, in other words, to calculate the probabilities of events comprised by these elementary events, because these elementary events are equally likely, we can do this by just counting the number of ways that the event can occur and then dividing by 36. Now I can also take that same table, and instead of writing down the ordered pairs, I can write down the value of the random variable. and that's what I've done here. So for example, if die 1 is a 1 and die 2 is a 1, then the sum is 2, obviously. If die 1 is a 2 and die 2 is a 1, then the sum is 3. On the other hand, if die 1 is a 1 and die 2 is a 2, then the sum is 3 as well. And you can see the structure here in the table. And so to compute probabilities involving x, all we have to do is count the number of ways that event involving x can occur and then divide by 36. And one thing I would point out, which is obvious of course, but the values of x range from 2 up to 12. So the possible values taken on by the random variable x are the integers from 2 to 12. Now let's consider the sample space of the original experiment, and for k going from 2 to 12 in the sample space of x, we're going to define some notation here. We're going to define the events a sub k being the set of all outcomes in the original sample space, all right, in S right here, So these are elementary events. I'm sorry, these are events. Actually, the subscript on these corresponds to the values taken on by x, and the event itself it corresponds to a subset of the original sample space for which that sum is possible. And so a sub k, for a particular value of k from 2 to 12, is going to be the set of elementary events, the set of ordered pairs from the original sample space for which the sum of those two values, the sum of the two coordinates, is equal to the value of k specified. So for example, for k equal to 2, for example, a sub 2 would be the set of ordered pairs ij such that I plus j is equal to 2. Well, obviously in that case I would have to be 1 and j would have to be 1, and that would be the only possible way that you could get a sum of 2. And so using that notation, these events can be expressed as subsets of the sample space S as shown below. So again, for k ranging from 2 to 12, the values in the sample space of X, what we've done is written each of these events as a subset of the sample space capital S of the original experiment. And since the 36 elementary outcomes in the sample space S are equally likely, the probability of an event such as A sub k can be calculated by counting the number of elementary events comprising the event and then dividing that number by 36, which again is the total number of elementary events in the sample space. And so the next slide shows how to use this approach to calculate the probability of each of the A sub k's, k going from this says 1 to 12, it should be 2 to 12. And so for the probability of A sub 2 is equal to 1 over 36 because there's only one there's only one elementary event in the sample space of the original experiment for which the sum of the two dice is equal to 2. The probability of A sub 3 is equal to 2 over 36 because this composite event contains two elementary events, and so forth. So you see how these probabilities are obtained by going back to the sample space of the original experiment and taking into account the probability structure associated with that sample space. And so using these probabilities, and note that this would be equal to, what this gives here is the probability that x is equal to 2. This gives the probability that x is equal to 3, and so forth, down to the probability that x is equal to 12. And so from this, we then get the PMF of the distribution of x. And so for every value in the sample space of x, we have a positive probability. The PMF evaluates to a positive value. It's strictly positive for every value of x in the sample space of x. And then the PMF is 0 at every other value that on the real line that is not in the sample space. So again, it's always very important to make sure that you specify this last part here, that for any value of x not in the sample space, that PMF evaluates to 0. Now, again, just to point out a few things about this PMF, it's defined at every real number because we have taken the time to include this last statement. It's now defined at every real number. The PMF is strictly positive at every point in the sample space of x, as we said. And then the PMF is 0 at any point that is not in the sample space of x. Now, what does the graph look like? Okay, well again, it's a series of rectangles. One rectangle for each of the values in the sample space of the random variable. The rectangle is centered over the value that it corresponds to, and then the area of the rectangle is equal to the probability associated with the value over which it is centered. Now, once we have the PMF, we can begin to we can construct the CDF, the cumulative distribution function. And if we look at this graph of this PMF for a second, we can see here that we don't start accumulating probability until we get to 2. And once we get to 12, we've accumulated all the probability there is to accumulate. And so we know that the CDF is going to be equal to 0 when we evaluate it at any value of x strictly less than 2. And we know that the CDF is going to be 1 when we evaluate it at any value of x greater than or equal to 12. And then for values between, starting from 2 and then up to and including 12, we're going to be accumulating probability based on where we are on the real line. All right, and so this is what the CDF looks like. All right, again, we are accumulating probabilities. All right, and we can tell here that it's going to be a step function, just as the CDF in the last example is a step function. In fact, you probably realize at this point that for any discrete random variable, the CDF is going to be a step function. Okay, so let's talk about a few characteristics of this CDF before we show the graph. So again, it's defined at every x on the real line. If you look at the values over which we are defining the CDF, specifying the CDF, there are no gaps. All right, regardless of whatever real number that we could potentially plug in here, there's going to be a row in this representation here corresponding to that particular value. So the CDF is defined at every real number. We can also see that it is non-decreasing. Okay, these values taken on by the CDF they never go down, right, as x is increasing. They either stay constant or they increase. The CDF is equal to 0 at every point to the left of the smallest point in the sample space, which again, that smallest point in the sample space of x for this example is 2. And then the CDF is equal to 1 at or to the right of the largest point in the sample space, which again is 12. All right, and so this is a graph of the CDF of x, where x is the sum of 2 fair dice. And again, we see that it's a step function. And then I would point out that, and I didn't really point this out in the previous example, but you probably discern this, that the height of the jump. So for example, if we look at the jump here at x equal to 6, going from this point, this step to this step, the height of that jump corresponds to the probability that x takes on the value of 6. So the step height or the jump height is equal to the probability associated with that point. And the other point that I would make is that you have these jump points or these steps or jump points only at the values of x that are in the sample space of the random variable. At every other point, or over intervals that don't include these jump points, the CDF remains constant at a particular value. Okay, so that finishes this example, and this is probably a good place to stop this particular video. And so we'll pick up the next example in the next lecture video.